Good afternoon, everyone. My name is Rogelio Sullivan. I'm with Power America. Thank you for joining us today for our monthly technical webinar series. We have the pleasure of hearing today from NexGen. But before I introduce our two, I want to give a couple of Webex housekeeping items. If the participant panel is taking up a lot of your screen, sometimes that pops up on the far right. You can just close that out, and then the presentation should occupy your entire screen. That's one thing. The other thing is that everyone is going to be muted throughout today's presentation. We have a lot of folks on the line, and that just cuts down on a lot of background noise. If you move your cursor down to the bottom of your screen, you'll see a bunch of options on the bottom. So I'd ask you to click on the chat box. It's the little, little chat will show up in words. And if you have any questions for me, type them in there. And that's where you will also type in all of your questions to the speaker. And then at the end, I'll read out all the questions aloud, and they'll answer them. So you can start typing in questions right away, so we don't have to wait till the end to answer any questions. Throughout the meeting, I'll type in my email address, so you all have that. And so if you want a copy of the presentation, I will be sending those out as soon as I can get them from the speakers. So with that, I'd like to introduce our two speakers today, Wolfgang Meier and Dinesh Ramanathan. Wolfgang Meier held several engineering and engineering manager positions in high-frequency device development, communication system, and ASIC engineering in Germany before joining Infineon North America in 2000. He held technical, marketing, and business development positions covering high-speed ASIC and read-write channel products before joining Infineon's power management product segment as a senior business development manager for power management IC and discrete power management. He's now the senior director of marketing at NexGen. Dinesh Ramanathan is the CEO and co-founder of NexGen PowerSystems. Prior to founding NexGen, he was CEO of Avigy from 2012 to 2016. He guided concepts to commercially feasible GaN-on-GaN vertical power transistors, the holy grail of power electronics. His team created groundbreaking intellectual property that resulted in 78 patents. And Avigy sampled GaN power devices to customers and partners like ABB, Bosch, Shindingen, and onsemi. And Avigy launched a systems concept, Zolt, charger for laptops and 2 mobile devices via direct-to-consumer online retail channels. Before joining Avigy, Dr. Ramanathan was the Executive Vice President of the Programmable Systems Division and Data Communications Division at Cypress Semiconductor. And my last final announcement, I forgot to mention that this webinar is going to be recorded and it will be posted to our YouTube channel by the end of the week. I'm required to notify you of that. And with that, I'd like to introduce NexGen. I think Mr. Meyer is going to speak first.
Actually, I'm going to just introduce the company in the very first slide, and then Wolfgang will jump in. So thank you, everybody, for joining this webinar. We appreciate your time. We're going to be talking to you about vertical GaN devices. We believe fundamentally that the full potential of gallium nitride is realized by vertical gallium nitride devices. And that's what this presentation is about. It will talk to you about the advantages, compare it against other product offerings that are power devices that are in the market. It will talk about how vertical GaN can be used in applications, the simplicity of the approach, and then we'll give you kind of a quick overview of what the status is and what the outlook is of this technology. With that, I'll hand it over to Wolfgang.
Hello, good morning and good afternoon. A pleasure to have the opportunity to speak about vertical GaN and the Power America's monthly webinar. And Dinesh has already given the introduction, so let me go straight ahead to the first slide. And let me know if there's anything, if you see anything, if there's any problems with the visual presentation here, and I can react right away. But anyway, here with the first slide, what you see here is the principal display of vertical GaN junction FET built completely out of gallium nitride. So that is basically the core of our products here. We have a junction FET which is built upon a gallium nitride wafer by adding a gallium nitride drift layer and then building the gate structure and the source structure completely out of doped GaN. So there's nothing in a complicated structure here. It's a very straightforward device. And the main point here is that in this device, the current flow is in vertical direction. So it goes from the drain, which is basically built upon the wafer, to the source, which is on top of the device. And the major differentiation to other implementations of GaN transistors, which you possibly know, is that in our case, the breakdown voltage here is completely determined by the vertical dimension of the device. So that is the only dimension which determines the breakdown voltage. There's no lateral dimension involved in determining the breakdown voltage and creating the properties of the device, which makes it function at high voltage. So with this device built up, we have basically decoupled the RDS on of a transistor from the breakdown voltage of a transistor, and this allows us to make very small devices which nevertheless have very high breakdown voltage. And we have shown in our lab that we can provide breakdown voltage in these structures up to 4,000 volts. Also, our product offering will start with 1200 volt devices. Another thing which we should mention here in this slide is that we are starting from gallium nitride wafers and building the whole transistor, meaning the different epi layers, homo-epitaxially grown epi layers, completely in our fab in Syracuse. So we have the full development process and production process under our own control, which is very important for moving fast forward in the development of devices. So let's go then in the next slide a little bit deeper into how the device actually works. So that is a segment out of the picture which I've shown you before. And here you see a little bit more in detail how the transistor is being controlled. Again, it's in essence a JFET, and we are creating a depletion region under the gate, extending into the drift layer. And in case that we have no positive bias of the gate source diode, here the depletion region extends into the channel itself, basically cuts off the source from the drain and cuts off the transistor. Now when we apply a positive bias above the level of the threshold voltage to the gate, then the depletion region is being reduced and the channel is being opened and allows the current flow from the drain to the source. So that is basically the main operation principle of our vertical GaN transistor. Should not come as a surprise for everybody who is familiar with junction FETs, which is a principle known since long, and which is a very established principle in a high frequency device. So it distinguishes us because of the simplicity of the process and the simplicity of the control from other gallium nitride devices in the market here. In the next slide, I'm then going to show a little bit of the electrical functionality of the device. What you see in the upper left-hand corner here is basically the very familiar output current structure of a transistor. So you see the drain current, how the drain current behaves in dependency of the drain source voltage with the gate source voltage as a parameter. That is a very familiar picture. And I should mention here all the diagrams here relate to the 85 milliohm device here. So we can draw a lot of current, and you see that in the area of 5 volt, the device is already in saturation. Lower left-hand picture shows the control functionality. So here we are holding the drain source voltage constant, and we are observing the drain current depending on the gate source voltage. And you see here that the threshold here is approximately at 1.2 volt. you see we have a large scale for the drain current here, so therefore the exact threshold voltage is not directly visible, but that is the region where we have positioned in our device the threshold voltage around 1.2 volt. On the lower right-hand corner, you see that we are drawing a small gate current when we are operating our device because we are biasing the gate source diode in forward voltage. But you see that with a gate source voltage of around 3 volt, which is what you recommend as the maximum gate source voltage in operation, we are just drawing 1 milliamp or so as the gate source control current. Or gate source current flowing into the gate source diode. What I should really mention here in this diagram on a lower right-hand corner is that although we are drawing a gate source current, the gate source current is basically a byproduct of the gate source diode which we are creating. The gate source current is not instrumental in basically opening the channel. The opening of the channel is just the function of the extension of the depletion region, but the gate source current is not instrumental in opening the channel and causing a drain source current to flow. And in the upper right-hand corner, last picture of this slide here is showing that we have basically a symmetrical device. So when we exchange or when we change source for drain and drain for source, the device still operates and draws and allows current to flow between the drain and the source terminal. And that basically resembles the function of a diode in your normal MOSFET, silicon MOSFET devices. So we have full reverse conduction here, but without the drawbacks of reverse recovery charges if we have reverse recovery here. So it's a very robust device here, no reverse recovery charge, very low losses when, or actually no losses when you change current conduction direction. So that completes the basic functionality of the device itself. And with the next slide here, I would like to introduce a major differentiation between the vertical GaN enhancement mode JFETs and other GaN devices on the market. As discussed before, when introducing the operating principle of the device, you see that under the gate extending into the channel, we have basically a diode structure with a depletion region and all the properties of a diode in itself. So this allows us to really create avalanching function in a gallium nitride high frequency switching device, which is not a property of other devices here. So how does its avalanche function work? Actually, there are two steps here involved. If we extend, if we exceed the breakdown voltage in reverse direction for the, let's call it gate channel diode in this picture here, then the junction breaks down, the junction is avalanching, and a small avalanche current is flowing out of the gate. By this current flowing out of the gate, we are creating a voltage drop about across the internal and external gate resistor, and this voltage drop across the gate resistor basically creates a positive bias, and then in the second step the channel is completely open and discharges all the energy from the overvoltage causing event directly through the drain source normal transistor function, which makes the device really robust, and we have a safe avalanche operating here. So next slide here addresses one of the elephants in the room, I would say. What distinguishes our device, our vertical GaN JFET, from the lateral GaN devices out in the market? And the first thing to mention here is that due to the vertical construction and due to the breakdown voltage dependency only on the vertical dimension, meaning only on the height dimension, we have effectively decoupled the RDS on and the breakdown voltage of a device. So as you can see in the small boxes on top on the vertical GaN JFET structure, if we go from 650 volt, for example, to 1200 volt, we only have to increase the height of the device, but not any of the lateral dimensions. We use the lateral dimension only to decrease the RDS on, and this allows us to create a real 3D device where we can modulate the breakdown voltage without modulating the RDS on. And this differentiates us from the lateral GaN devices, where the breakdown voltage is mostly determined between the distance between the drain and the source. And here you see already that one of the lateral dimensions is occupied by modulating or creating the appropriate breakdown voltage. So if you increase the breakdown voltage, you have to increase one of the dimensions in one of the lateral dimensions. This increases the RDS on, and in order to bring this back, you have to make your device larger. So this is depicted then in the boxes on the above the gallium on silicon, for example, HEMT, and here the breakdown voltage is directly coupled with the lateral dimensions of the device and makes the device larger here. And on top of this, as we have mentioned before, we have a device which avalanches, and this is not a property of the lateral GaN devices on silicon or silicon carbide. We avalanche safely, and there's no increasing of leakage current, which is the case if you apply overvoltage to a lateral GaN device. It's all its complications which can arise from this. And in addition to this, because everything in the vertical GaN JFET happens within the bulk of the device, we are very insensitive for that. We are very insensitive to what is happening on top and on the bottom of the device. So we can cool our device from top and from bottom, which makes the package integration and the power density, makes the package integration easy and the power density very high. So this slides put the vertical GaN device, our vertical GaN device, a little bit in perspective to all the other technologies on the market. And we have provided a comparison here between the different technologies on the basis of a die which is capable to carry 30 amp of drain source current here, or current in general. The first thing to note here is we can provide this current carrying capability on a 2 square millimeter die, which is also capable to withstand 1200 volt breakdown voltage. And this is a property which is only being shared with silicon carbide, but at a much larger die size. Silicon IGBTs, of course, can carry this breakdown voltage as well, but at an even larger die size. So that is one of the major differentiators. And because we have this small die size, the capacitances in our device are very small. And this allows us to address very high switching frequencies. And the switching frequencies can go up to 10 megahertz and more, which also sets us apart from the lateral GaN on silicon transistors. And we have a distinct advantage here, which we also show in one of the further slides here. Because we have the large band gap, comparable and larger than the silicon carbide, actually, we can address the same temperature range, and which is much higher than what we can do on the silicon devices. And if you look at the commercial dimensions here, first of all, we have a simpler device with lower processing steps here. And because of the small die size, we can still maintain a close to cost parity between the established silicon technologies here, which you see in the comparison of the relative cost for the 30 amp die, and we believe that we can achieve cost parity in the next year or so. Major contributions here is simplicity of device processing, small die size, which compensates then for the currently still higher gallium nitride wafer cost, but we expect that this wafer cost will come down significantly because we can still benefit from scaling of the wafer cost, where silicon devices usually have to reach the bottom of the wafer cost. So you can expect our device become more cost competitive over time. Now I would like to go forward a little bit into the application domain of the device itself. So one of the major benefits of having this gate source diode and the control over the gate source diode is that we can employ readily available low-cost silicon MOSFET drivers in order to control our device. So we don't have any specific requirements on specific drivers or driver structures. And how this operates is very simple. We are basically carrying a small current through the gate source diode of our device. And then when the silicon MOSFET driver delivers an on voltage, let's say 10 volts or so, then in a static case, we control the gate source voltage of our device through a voltage drop over the resistor R1 in a static case, opening up the channel completely. But in a switching situation, you want to have a punch opening the channel quickly and potentially driving the RDS on voltage, so the RDS on resistance down significantly, and this can be done by this RC network over C2 and R2, which gives basically the opening situation or the opening transition a punch. And it serves also a purpose when you shut off the device, because then you're driving the voltage of the MOSFET driver down to 0 or in the negative domain even, and then you provide a negative, short-term negative voltage through over the gate source diode, which then helps to shut down the gallium nitride transistor really quickly. But the main point here is that all you need in order to control our vertical GaN JFET from a silicon MOSFET driver is just 3 passive elements, and then you can integrate your gallium nitride vertical GaN device into your existing circuitry. So that makes the transition, number one, very easy, and you can maintain all the experience, all the investment which you have done into your drivers, and you can take advantage of readily available cheap MOSFET drivers. The next slide does a little bit more explanation, but it addresses a topic which may come up, that a device with a very low output capacitance may not be as beneficial in zero voltage switching applications where the output capacitance is perceived as not so very much important. But if you look a little bit more in detail into the operation of an LLC, and we have done some studies here on that one, then you will see that the output capacitance is directly related to the dead time which you have to employ before switching, let's say, from a high side transistor in an LLC configuration to a low side transistor. And we have done some simulations based on our device models and compared this with what is known from lateral GaN on silicon devices. Modeled the two devices the output capacitance of the two devices is piecewise linear functions, and the outcome of this simulation you see on the bottom right-hand picture. The very thick lines, dotted or normal lines, they represent the voltage at the switching node, and the thin lines below them, they represent the actual drive situation, the drive control voltage of the high side and the low side FETs here. And what you see, okay, I should say the green lines, the solid lines, this is the vertical GaN FET, and the dotted lines is the lateral GaN FET. And what you see is that on the basis of a 1 megahertz switching LLC device, we only need a dead time with a vertical GaN device of 15 nanoseconds between the switch turning off the high side and turning on the low side in order to maintain the zero voltage switching situation. Whereas the lateral GaN device, which we have used as a reference, state of the art, and I would say best in class, actually needs 32 nanoseconds of dead time. And if you go to silicon devices, the dead time becomes even higher. So even if this proves the point that even in a situation where you say, okay, we have zero voltage switching and the output capacitance really is not this important, the high output capacitance of traditional devices creates a large dead time, and that has two effects. So first of all, if you go to higher switching frequencies, you're losing more and more of your cycle where you don't have the whole system under control. So the controllability is an issue. And if you spend much more time in dead time, so to speak, then the gain of your device, of the LSC stage, is being compromised, is lower, and you lose some of the regulation capabilities. Of course, you can make it up by increasing the circulating current, but when you increase the circulating current in order to bring down the dead time of your LLC, then you increase the I2C losses. So here again, you may make the argument in zero voltage switching situations, the output capacitance is not very important. But if you look a little bit deeper into such a construction and such an application, you see that you're losing controllability and regulation. So that is a major requirement when you go into application where you, for example, in an LLC want to operate at 1 megahertz and higher and reap the benefits of higher switching frequency and smaller components and increasing the overall power density.
Excuse me. Excuse me. Someone suggested ask your cursor on the screen to make it easier to follow which particular graph or table you're referring to.
Yeah. Okay.
Yeah.
That is a very valid point. Thank you for reminding. Yeah.
Okay.
So what I was talking about really quickly, on the upper right-hand side, you see the principal schematic of an LLC device. Then on the graph in the middle, that is the output capacitance of a lateral GaN on silicon device. And we have used the PWM, not PWM, a piecewise linear approximation. And on the left-hand side of this picture, you see here the output capacitance of our vertical GaN device. Again, we have used the piecewise linear approximation here. Then, if you observe the switching of the LLC application here, the solid lines and the large dotted lines, these represent the output voltage of the switching node between the two devices here, and the smaller solid line and the smaller dotted line here and there, these represent the control voltages for the high side and the low side switch. And what you see here is that in order to achieve zero voltage switching, you need, after you have turned off the high side transistor, you need to wait until this switching node rings down to 0 before you turn on the low side transistor in order to have what is perceived lossless switching. But you have to, in case of a device with a large output capacitance, you have to spend more time between shutting off the high side transistor and turning on the low side transistor. And that is the daytime I was talking about. So this completes the application overview. And in the next 3 slides, I would like to hand over to Dinesh. And Dinesh, you may want to guide me when you want to have your slides being changed.
Sure. Thanks, Wolfgang. So let's go to the next slide. So after having looked at the way the device gets driven, the properties, the output capacitance properties of the device, we then jump into 2 key case studies that we are working on, and then the third one comes up in the next slide. So the first case study is a power supply platform that we're building internally. The first product or reference design that we build is a 240-watt power supply, and the same architecture will apply to all power supplies between 75 and 240 watt and beyond. This power supply is going to be 50 smaller than the existing power supply, which means its power density is going to be twice the power density of any product that's available in the marketplace today. And it will suffer no increase in cost. So that's the first power supply platform that we're putting together with the technology and the drive capability that you've just seen. The same technology, of course, also applies to 300 to 700 watt power supplies for various appliances, and from 1.2 to 3.4 kilowatt for servers in data centers. So we're at that entire market with this first reference design of 240 watt that we're putting. And we have 2 partners that we're working with to realize that design. The second case study and the second reference platform that we're putting together is in the LED drive platform. So we're making a 20-watt LED drive. Value proposition that we there is that the LED drive platform cost, the overall system cost, actually goes down by 10%. Now, everybody knows that the LED drive platform is typically one of the most cost-sensitive areas of the market. And the point we're trying to make here is that we can actually participate in that cost-sensitive market, add value on cost. So that big push from our. Let's go to the next slide. All the way from them, there's an electrical vehicle platform that we've been together. We have partners in Europe that we've been working with, and subsystems inside the electric vehicle that we participate in. The first subsystem is this is where you take a wall socket and you charge the battery that's there inside the electric vehicle. The second is the DC-DC converter. Here you're taking power from the battery and then supplying it to the rest of the equipment that's inside the car, the air conditioner, the heater, the power doors, power windows, your headlamps, your dash display, everything gets powered by the DC-DC converter. The third one is the AC-DC inverter. You're taking power from the battery and AC motor in this marketplace. So the numbers that you're seeing around the gallium nitride block is the potential size reduction and with this entire thing together, plus the increased efficiency that we bring to the table, we're able to go ahead and reduce the cost by roughly about 20%. And then this number, of course, has come about by the that we have been having with the folks that work in the automotive space, along with our strategic technology. Go to the next one. So the devices that Wolfgang has been talking about are built in this fab that we operate. It's a fab that is dedicated to GaN. It is 66,000 square feet large. It has a 20,000 square foot clean room. It's ready to scale. And we're in the process of taking the devices that Wolfgang talked about. At this point in time, I'll hand it over to Wolfgang. This fab is located in upstate New York, and we were lucky to be allowed to keep running this fab even during the current downturn.
Okay, so after introduction of the fab, let me just show you what we are doing in the fab here after all the cartoonish introduction from before. You can see on this slide here gallium nitride really in action, and that is actually a slide which we have and a demo which we had prepared to show in APEC, but unfortunately this couldn't happen. So let me show it to you instead here and at this opportunity. So what you see here is basically a combination of a gallium nitride vertical GaN FET and the gallium nitride vertical diode here in action in the boost converter, and it shows you several things here. First of all, you see here the device switching at 900 plus kilohertz and operating at 400 volt voltage. So with a load, with an inductive load as typical in boost converters. So what you see here is a proof of existence that the device is real, it operates, it switches at high switching frequency, and it switches at high voltage. So there's a real device, not only cartoons as shown in the slides before. There's also, we can also show here the setup, that we are driving from a standard silicon MOSFET driver without any fancy specific driver circuitry here to drive our transistor. And also, based on the same process technology, we are able to provide a vertical GaN diode at high breakdown voltage, which challenge the, if you want to say so, supremacy of silicon carbide diodes. And that is vertical GaN, if you want to say so, in action. Next slide.
Yes, let me add one more comment to this.
Yeah, I'm here.
Wolfgang?
Yeah, you should be able to see it.
On this slide, there's another key parameter about, which is the capacitance of that GaN diode. Capacitance of the vertical GaN diode is so small that it actually performs better than a silicon carbide Schottky diode in that particular circuit. So the point here being that if you start running circuits at high switching frequencies, use vertical GaN, just PN diodes, performances than most of the diodes that are there in the marketplace today.
That is also shown in a slightly different aspect also here on this slide, and I hope it stabilizes. So what this slide shows is a verification of our major claim that vertical GaN avalanches, and we have had our diodes which have the same buildup as transistors, actually, in an standard avalanche test situation, and this has been tested by Virginia Tech. So it's a third party which verifies the avalanche capabilities here of our device. And what you see here on the upper right-hand picture here is basically the oscilloscope plot of a standard avalanche setup. So basically, when we switch off the current through the inductor, then a high voltage builds up over the diode, and the avalanche breaks down. The voltage goes up to 1600 volt when the avalanche actually is happening, and then basically the energy stored in the inductor is being discharged to the avalanche breakdown in the diode. And on the lower right-hand picture, you see how our device, which is actually the dark purple one here, behaves in comparison to silicon carbide, to different silicon carbide technologies. And you see that we are breaking down at 1600 volts. That is as described in the oscilloscope picture here. But you see also that our leakage current is much lower than many of the silicon carbide devices here. So they raise in leakage current until the point where the avalanche actually happens. But our leakage current stays, the gallium nitride vertical GaN diode leakage current stays relatively low until the breakdown actually happens. And that is another property which distinguishes us from the silicon carbide devices, in addition to the much lower capacitance which we have and which enables then switching at higher frequencies. We are in the process of building our transistors, and also in order to verify the technology and verify our potential future diode products, we are exposing gallium nitride vertical GaN diodes to long-time reliability tests already now. And we are using the vertical GaN diode as a reference for our device, our transistor device as well, because as you can see here in the upper right-hand corner, we are employing the same build-up for the diode as we are using in the transistor construction. So we are starting from the gallium nitride wafer. We are building the drift layer, the homoepitaxially grown drift layer on top of the gallium nitride wafer. We are employing the p-dope GaN region in order to create the gate or the anode for the vertical GaN diode. So it's essentially the same build-up, and by performing reliability tests, in this case here the particular high temperature reverse bias on this structure, we make sure that our major processing steps are verified and capable to deliver the reliability which we are targeting for our device portfolio. So what you see here are data after 1,000-hour HTRB tests at 960 volt reverse bias and 150-degree centigrade. And you see here different readouts over time. There's no major deviation from the starting readout to the 1,000-hour readout, and we're continuing this test ongoing in our fab. Different lots are being tested all the time here. That confirms basically that our major device build-up, the major steps of the device build-up are solid, and there is no hidden uncertainties, the hidden reliability issues here in the device construction. Next slide shows an outlook of our product portfolio. We are starting out with releasing 1200 volt devices in the RDS-on range between 85 milliohm and 290 milliohm autumn this year. So we are targeting Q3 for the release of engineering samples, but in fact for customers who are already working with us right now, we are releasing early engineering samples in the next weeks here. So they will get an early glimpse on what we can deliver, and the release of a public broader release of engineering samples is targeted for Q3 this year. As I said, we are starting out with 1200 volt, with a 1200 volt portfolio. But due to the fact that the breakdown voltage is mainly dependent on the thickness of the drift layer, we can immediately, after the initial release of the 1200 volt versions, we can release the 700 volt version for a different set of applications. And that will then be followed in 2021 by a lower voltage version, 200 volt, as our current target. And in the 2022 region, we are planning to integrate drivers in the same package. That isn't a big deal for us because the devices are relatively small, as you have seen in the previous slides. So there's enough room in the package to integrate a driver, which makes the overall device construction, the overall applications construction, again, much more dense because one of the additional components is basically integrated in the package. Here on this roadmap, you see that we cover the range of 290 milliohm to 85 milliohm. That is our baseline portfolio, but we are working already on higher ohmic devices in the region of 1 ohm, 500 milliohm to address the LED applications which Dinesh mentioned before. So that completes the overview presentation on vertical GaN. I hope you got all the information you needed. We have a website running where, of course, we have a website running, but there's much more information there. And we, Dinesh, myself, we are available for questions. We have the email addresses, I think, mentioned on your introduction here through Power America, but it's also on the website. So if you have questions, feel free to contact us, and we're happy to get in touch with you. That concludes the presentation so far.
Well, thank you very much, Wolfgang and Dinesh. That was an excellent presentation and a great overview of some of the advantages of vertical GaN. I was particularly interested in seeing some of the size, weight, and cost advantages in the automotive application. So that's pretty exciting to see. I guess we'll be seeing some of that in the near future. We have some questions already that people have typed into the chat box, so I'll start to read those out now. And I would encourage all the other participants in the webinar to pull up the chat box by scrolling over the lower half of your screen and typing your questions in there. Okay, so the first question is, GaN bulk wafers are very small and very costly. How do you want to make vertical GaN commercially viable?
So let me take that one. This is
Dinesh, do you want to answer this question?
Yeah, let me take that one. So GaN substrates are mythically supposed to be very small and very expensive. So let me give you the facts. The facts are that GaN wafers are at 4 inches right now. And the 4-inch wafers are being used pretty significantly in the GaN LED space. And the costs are not as high as people have been talking about. So as I pointed out, with the cost structures that we talked about and the small die size that we can achieve, our devices will actually be competitive with the silicon devices in the market.
Okay, the next question is, the device structure reminds me a lot of the enhancement mode JFET design from SemiSouth, which met major production issues due to the critical dimensions involved, e.g. source finger width had to fall into a very tight window. Can you comment on the manufacturability of this process for GaN eJFET?
Yeah, that's a very good question, and the only way for me to answer it is that we've actually jumped over those manufacturability issues. We've made sure that we have the right tools in order to enable us to get to the right fin width size, which is what you were talking about. We've also made sure that we have right doping concentrations, and then we are making sure that the areas where you have high field strength are actually managed appropriately as well. So it's not just the width of the fin that's actually managed quite effectively with our stepper, but it's also a bunch of other things which we have taken care of.
Okay, thanks. Next question. As the die are extremely small, how do you get the high currents in and out?
We actually end up cooling the die. Right?
Okay.
So, yeah, go ahead, Wolfgang.
I mean, the current density is not unusually high for a 2 square millimeter die, for example, and what usually limits the current capability is the thermal resistance between the die itself and the package. So you don't want to overheat the whole system. And there's nothing different here in our construction from what is used in the established, let's call it established device domain. More of a concern is most likely how you contact the device to your package. And here we are employing clip technology, for example, which is also an established technology in the DFN space, and we can do the same also for the TO247 space. So we don't see anything unusual here in the construction of our device inside of the package.
Rogelio?
Any other questions?
Yeah.
Hello?
Rogelio, are you there?
Dinesh, you can hear me, right?
Yeah, I can hear you, Wolfgang. Can you hear me?
I can hear you as well, yeah.
Okay, so I guess we're missing Rogelio.
So Denise, this is Victor. Can you hear me?
Yeah, I can hear you clearly.
Yeah,
Okay, so I'll just ask my question directly since Rogelio might have some trouble with the connection. So your structure, it's obviously, apparently a vertical JFET where you have the two P gates, and as you apply a gate voltage, those P gates, the depletion region expands and chokes the channel, blocks the channel,
Yeah.
and it blocks the high voltage. That's, I guess, the standard mode of operation, and it's a very well-known device. I've made a ton of those devices in silicon carbide. So my question to you is, as you go to higher voltages, okay, so as you go from 650 or rather 1200, where it really makes a lot of sense to make the vertical GaN, you go from 1200 to, let's say, 3.3 kV, then there's a much higher voltage that you need to block. So the depletion region overlap in blocking mode has to be very, very strong to stop the tunneling. So the P plus gate areas need to be spaced closer together in order to be able to block the higher voltages. And that has the result of having a much more resistive channel. So does that limit how far you're going to go in voltage? I know you're looking at 1200 volts, but then, if you go to, let's say, 4 kV, 6.5 kV, or even 10 kV, then those gates need to be very, very close in order for the depletion overlap to be strong enough to block, the 10 kV voltage. So what is your, and of course this is for Wolfgang as well. What is your view on that?
So you're right. But the way we are thinking about it is, as we get to higher and higher voltages, the structures that we will end up deploying at that time may be different than the JFETs that you're seeing right now, right? This JFET structure is very, very appealing to us because it takes us, all the way to 1700 volts, 1200 volts, down to 600 volts, and even 200 volts, and it works, exceedingly well. But yeah, if you have to do 10,000 volts and beyond, we'll probably end up thinking of a different structure. And by the way, we haven't really spent too much time on that particular effort. We've kind of focused on, what's the markets that are important for us, which is 1200 volt, 650 volt, 200 volt, and then maybe push it up to 1700 volt at this point.
Okay, so just one last question. Between the 200 volt and the 1200 volt, right? The overlap for the 1200 volt needs to be significantly, bigger in order to block 1200. Have you seen a sharp rise in resistance between the 200 volt channel resistance and the 1200 volt channel resistance?
There is, but then we actually compensate for that, by controlling the doping.
Okay, thank you. Appreciate it.
Yeah.
Okay, I'll continue with the written questions now. Sorry, I got bumped off the audio for some reason. With a vertical GaN device, you lose the benefit of integrating more transistors and other circuitry monolithically. With lateral GaN, that is possible, as people like Navitas and EPC are showing. How do you see this issue?
So I think the argument that you have to make is the following. The gallium nitride devices in court are more expensive per unit area than silicon devices. So if you want to do integration, you should make the circuit that you want with the type of material that gives you lowest cost from a dollar per unit area perspective, and that would be silicon. So I think the way I think about this is, keeping GaN as a monolithic device, which allows you to get the full benefits of gallium nitride, and use silicon for all the other logic circuitry that goes around it, or even to some extent the analog circuitry that goes around it, is the best way to take this approach. So that way you keep the costs under control rather than use more expensive material to actually make circuits, which you can actually make with cheaper material.
Okay, next question. As stated earlier, the avalanche breakdown condition transitions into the gate becoming positive bias and then the device turning to on state. Are these two operating conditions evident within the avalanche data given?
The avalanche data given here was for the diode. So we are performing these tests, but we have to provide some slides here regarding that one. But yes, they are evidence. So we have proof that this is really happening.
Okay, thanks. Next question. How many devices can you put in parallel?
I mean, that is potentially an application question. So it's not really I don't perceive it as a question of the devices itself, because the application needs to make sure that the current is equally distributed between the different devices which you put in parallel, and of course you need to provide the sufficient stable and powerful driver setup if you put many devices in parallel. So that is basically the same. There's no difference in parallelizing devices on our side than with any other device technology.
Okay, thank you. Can you discuss some of the processing challenges in GaN devices from Applied Materials?
Yeah, sure. I'll tell you one simple thing. The GaN wafer is transparent, so you have a bunch of things that you have to worry about. Plus, there's another question that comes about regrowing. So we actually regrow. So then you have to worry about what kind of alignment marks you have on the device, especially when you take the same wafer through a high temperature regrowth. Yeah, so there's a bunch of processing challenges that we had to overcome, but they've all been overcome with standard equipment, and we operate all these standard equipments in their operating area. We're not pushing limits on implanting and the temperatures of implanting, which other technologies do.
Thanks. What roadmap on GaN substrate size do you see?
So today, 4 inches is available in plenty with a significant amount of volume and the ability to scale that volume. Some of our vendors have actually already shown us 6-inch GaN wafers as well. So that's as far as I can tell you right now.
Okay. How are you achieving selective area P-GaN for the gates? Are you etching and regrowing or somehow able to successfully ion implant, magnesium activate?
No, we regrow.
Okay. As vertical GaN seems to be so good compared to silicon carbide, why are you just offering small current devices? Also, how would you address the second source issues when supplying to automotive companies?
So let me take the first one first. That's because we had to start somewhere. So an 85 milliohm device or a 25 to 30 amp device is a place to start. And then obviously our roadmap will include, increasing that to 45 milliohms, and then, making it even, be able to provide even larger amounts of current. So that's part of our roadmap. That's number one. Number two, second source. Second source is always an issue, is really what boils down to is one of two things. You need second source in order to keep price under check, or you need second source in order to make sure that the supply chain is appropriately managed. So we believe that the second source can be provided by making sure that the supply chain is managed appropriately. And that's the discussion we are having with automotive vendors at this point.
Let me just jump in regarding and complete or complement the device size and current carrying capability here. So there is no inherent limitation in small RDS(on) or higher current capability. It's just a commercial discussion what we want to address for the first devices here. That's all.
Oh, thanks, Wolfgang. So let me also point out that we've made diodes which were able to carry 200 amps worth of DC and 400 amps worth of pulsed current through them on a monolithic die, right? So the ability to carry a significant amount of current exists, and we've actually proven that.
Okay, what is the thickness of the vertical GaN?
So let me give you two answers to that. Wafer thickness, if you're looking at that, is about 450 microns. And then thickness of the material depends on what type of breakdown voltage you're trying to achieve. There are a bunch of papers out there that you can read, but I'll give you a rule of thumb. Rule of thumb is about a micron per 100 volts.
Okay. In vertical JFETs, as the blocking voltage rating of the device goes up, the gate spacing is typically reduced to block that higher voltage, leading to a more resistive channel. What is your experience with this?
We covered that, Rogelio. That was my question. This is Victor. We covered that while you were away.
I'm sorry. Okay, then next question. For slide 11, you mean 20% reduction for the component charger, DC to DC inverter, and not the overall vehicle?
No, actually the overall vehicle, because the efficiency improvements allow us to get more mileage on the same battery, and the weight reduction also contributes to getting more mileage on the same battery. So the overall reduction comes from reducing the components, the cost of all those power subsystems, and of making sure that the battery becomes smaller.
Okay, that's pretty impressive. Okay, next, related to Victor's question, to improve the ability to pinch off the channel at higher blocking voltages, a lateral channel VJFET can be used. Have you compared the performance between vertical channel and lateral channel architectures?
No. Well, yes and no. Yes, we have, and I don't have an answer to have compared it with the right level of current densities. The problem with the lateral channel, as you pointed out, lateral channel was one of the things that we used in Avergy. The die size becomes bigger, right? You don't get an optimal die size. So, FYI.
Okay. Do you plan a Schottky or MPS diode to lower VF?
Yes.
Okay, next question. Higher voltage requires higher resistivity and thicker epi, which both raise resistance. So vertical devices still expand laterally with voltage rating just as much as lateral devices. I guess that's a comment, not a question.
Yeah, that's not entirely correct. So we'll just leave that as a comment.
Okay. Could you comment on the vertical hemp device for a high current device such as 200 amp? In other words, instead of paralleling many discrete devices?
No, I mean, I don't know how to comment on it because we don't make vertical, we don't make hemps, right? So.
Okay. What is the voltage rise time of this device?
Wolfgang, you wanna answer that one?
Yeah, I'm not sure if I understand the question correctly. I mean, if you want to, if this implies how much dV over dt can we afford without the device being destroyed. I don't have an exact number here, but it is very high and absolutely comparable to what you see in the market. So we have not seen any dV over dt issues in all of our experiments, even at very high switching frequencies.
Okay, what is the specific RDS on of 1200 volt active area and 650 volt area devices?
Okay, I don't know how to answer that question. So if you have a 650 volt device, then the epi thickness that you need to grow is smaller. Therefore, the size of the device actually becomes smaller to achieve the same RDS-on. Because the resistance that you're seeing from the thickness of the device is gone down because you've actually made it thinner. And I'll just leave it at that, but you can kind of make some proportional adjustments about how much resistance comes from which part of the device, and then do a quick computation to see how small the device would become. It doesn't scale linearly, compared to the current that you want to run. The voltage has an impact on the size of the device as well.
Okay, is the epitaxial regrowth done in MOCVD, MBE, or other means? Is it regrown P-GaN or N-GaN in your device current structure?
Current structure, we are regrowing P-GaN in an MOCVD environment.
Okay, thank you. Okay, next question. How come lateral hemp has a worse RF performance than vertical devices, according to your slides?
I mean, the simple answer to this is our devices are much smaller and have lower COSS than comparable lateral devices of the same RDS-on or current carrying capabilities. So, and if you have a smaller COSS, smaller capacitances, your high frequency properties or the applicability of such a device in a high frequency environment is much better than if you have devices with larger capacitances. And that's the base. That's basically the basics of how we can prove that we are switching more efficiently at higher switching frequencies.
Okay, are there any unique considerations for space radiation environments?
I don't think so. Just the wide band gap allows you to kind of, be more space rad or rad hard if you want to think about it that way. We have not done, and I want to be specific on this, we have not done any rad hard experimentations on our device yet.
Okay, do you see bulk GaN for RF device application?
Yes.
And the last question, could you elaborate on the heat sinks used with these GaN devices?
I'm not sure if I understand the question correctly, but the heat sink is basically a property, or is connected to the package itself. For the construction of for the integration of our device into a package, we employ the usual techniques, and we can even use contacts on top of our devices to the top of, in order to achieve topside cooling.
Okay, one final question. How is the drift layer grown?
MOCVD.
And another one just snuck in. GaN has not so good thermal conductivity versus silicon carbide. I guess that's a comment, not a question.
Yeah, I mean, you're right, except the thickness of the material that you use that end up conducting, from your device to the package or to the board is also important, and we actually thin our material pretty significantly. So that's maybe one way to think about it.
Okay, thank you again very much. That was an excellent presentation, and thanks to all of our participants for all of your great discussion and questions today. Really appreciate your time, and we look forward to seeing you again in June. We still haven't confirmed a speaker, but we hope to have another webinar in June. coming up in the beginning to the middle of the month. So
Great.
thanks very much.
Aurelio.
NexGen. Yep.
Thank you very much, Aurelio, for conducting this, and thank you for inviting us. Thanks for everybody that participated. Again, be safe, everybody. Thanks.
Thank you very much.
Thank
Have
you.
a great day.
You too.